Next up, we've got Gerrit Bruhaug. He's a PhD candidate at the University of Rochester and performs research at the Laboratory for Laser Energetics on ultra-fast radiation sources for probing high energy density and inertial confinement fusion experiments. Before coming to Rochester, he obtained a BS in nuclear engineering and physics at Idaho State University. His talk is X-ray and gamma-ray beam interstellar communication and implications for SETI.
Hello, everyone. Thanks for having me here. I will be stepping in for Lucas Beveridge. He's the lead author on this, and I definitely want to shout out to Lucas that most of this is his work. My input is that I make powerful radiation beams, and I gave him a lot of feedback as to how we could what sort of realistic X-ray and gamma-ray sources we could imagine or build or already have today. And just a quick about us, Lucas is the senior nuclear engineer at Atomos Space, which is a startup trying to launch reactors for all sorts of fun future things. And then, as mentioned, I'm at the University of Rochester. So to start the entire concept here, high bandwidth communication is, of course, important for interstellar missions. We can all imagine why. We would love to be able to talk to other stars. If we imagine we're sending out settlements, we're going to want to talk to each other, and we might want to say more than, just SOS. Visible lasers seem like they have potential for high bandwidth communication over a couple light years. And as you start pushing those distances out, the requirements for power just scale through the roof. And radio, you're in the terawatts, which maybe future civilizations don't mind. But I don't know about you. I might not want a terawatt radio source near where my cell phone is. Much higher bandwidth is needed for any colonies, generation ships, things like that. And X-ray and gamma ray lasers look like a better option due to the diffraction limit, which is the equation I'm showing here, where you see spot size versus wavelength, size of our optics, and distance we're looking. And you'll notice that as we can get a smaller spot by just making the wavelength smaller, and I say just, but it does help quite a bit. And especially when you're looking at, many, many light years of distance, it helps a lot. The main focus of this work is actually what would we expect to see, and how would we design detectors to look for others X-ray communication. So before diving into that, let's just spend a little more time as to why X-rays or gamma rays, because SETI famously has always been focused on radio for very good reason. Radio is a well-established technology, and especially early on, it was kind of our only option to go listening. So if we look at wavelength, the longest wavelength I would call an X-ray is about 14 nanometers. Radio is in centimeters to meters. If you remember that previous equation, many orders of magnitude difference here. And I can keep driving that wavelength down. 14 nanometers is what we use to make computer chips right now with EUV, but we have picometer X-ray lasers right now. Plasma frequency is much, much higher for X-rays than radio. And that's important because your signal can start to be distorted by the interplanetary medium or interstellar medium. The plasma is not dense, but there sure is a lot of it. X-rays and gamma rays will not notice it whatsoever and can in fact go through relatively dense regions of space without much worry. And then how are they easily generated? Radio, of course, is very easily generated. We all have radio generators in our pockets right now. X-rays, we're getting there. Especially when it comes to coherent sources, it's still a relatively young field, but they're not. This is not science fiction. And then are they easily detected? Yes to both, although when it comes to X-rays and gamma rays, it's easy to say I got one. We're still getting everything worked out to do all of the very clever tricks that we have with radio communication. But once again, it's a young field. So a little more background on it. This has been proposed before. We don't want to try claiming that we're the only people to have thought about this. There's actually been testing of X-ray communication up on the ISS. There's been quantum communication experiments with X-ray communication, and it's been proposed for SETI from a method, or in light of something similar to the previous speaker, the idea of modulating neutron stars or things like that. and looking for artificial X-ray source, or what we thought were natural X-ray sources being modulated in an artificial manner. The technology is well established for X-ray lasers, and I'll talk about that on the next slide, but it may be part of the reason it hasn't been talked about as much. Is it 40 years ago it wasn't there, and now we have quite a lot of capability in this. Beams can be modulated to encode information with AM, FM, even phase control is now available if we keep our wavelengths quote-unquote reasonable. And there's potentially very high bandwidth. So this plot is comparing what Voyager is getting, Voyager at 8.4 gigahertz at 100 AU versus received power at 1,000 light years, both of them with a 23-watt transmitter. And we're plotting across photon energy. The orange line is Voyager, flat because it's not changing, and the blue line is scanning across what our X-ray laser can get. And you'll notice the X-ray laser can go much, much further and send quite a bit more. And in theory, we should be able to, and this is with a 1 centimeter beam waist, I might add. So there is effectively no focusing optics. I'm just making the X-ray laser and letting it expand due to diffraction. Anyone who does any optics knows that I could expand the beam and get a better result in the end. And there's potentially high bandwidth. If we look at 414 keV, and that's a line that's important because it's not going to be naturally out there. There's a lot of X-ray, or not commonly naturally out there. There's a lot of X-ray and gamma ray sources in the universe. 414 keV is the gamma ray from plutonium-239. That is not an isotope you're going to see much of. It is not a gamma ray line you're going to pick up on your gamma ray spectrometer unless there is plutonium nearby. So it would be kind of the X-ray version of the hydrogen line. In theory, if we did just on-off transmission and we had perfect transmitters, we could get an incredible bit rate, but this is a little too simple. But that shows you kind of the upper bound of what could potentially be there with no optimization. Either one of us are communications focused people, so I'm sure you can do better. Focusing on the X-ray sources a little bit, current day coherent X-ray sources already meet some of the requirements for this. They arguably meet all of them if we were willing to spend a bit of money to make our X-ray communication system up in space. We have tens of EV to tens of keV photon energies and tens of watts available. There are actually MEV, they're not fully coherent, but at least focused gamma ray sources as well in the hundreds of milliwatt ranges, and there's potential to scan that up. So we can really cover the full gamut of photon energies of interest. And these are, in the X-ray range, they're fully coherent, and like I said, full polarization control, which is important for encoding more information. And X-ray optics are available. It sounds wild, but if you go on the SLAC website, you can find all sorts of X-ray optics, and at the lab that I work at, we make X-ray telescopes, and we can get sub-micron resolution on ICF implosions with our X-ray telescope. So this is a well-established technology, and we could really drive whatever I'm showing you here further by just adding optics. Once again, this is no optics. So some examples, LCLS-2 at Stanford. This is a nearly 30-watt X-ray laser, fully tunable, really impressive bit of machinery. Kilometer scale, though. You could conceive of putting it in space, but we might not want to. A little more exciting, CXFIL, which is coming very soon in Arizona. It's the same technology using laser interference rather than magnetic undulators, and they expect to roughly match the output of SLAC in something that would fit in this room. And now you start thinking maybe we can communicate in space with these X-ray lasers, and it wouldn't be so wild to imagine that being a popular method of communication. So the implications for SETI are that this looks like a very promising way forward, and it might be a very promising way to communicate, especially over really long distances. So if there's other civilizations out there talking to each other or to colonies or just trying to find other friends, maybe they're beaming in coherent X-ray or gamma ray signals. And of course we wouldn't have heard them because we're not listening. So the main point of this work in the follow-up paper that'll come out is we had to determine how would you find an artificial X-ray signal? What would you actually be looking for? And Lucas generated a Python code to simulate detectors and realistic detectors and signals. He's a nuclear engineer just like me, so he's very familiar with all of this. And then he sent a whole bunch of different files through, as well as random signals to get the same treatment and then compare through this analysis. And the real signals and random signals were compared using their relative entropies. So this gets into information theory. I'm going to ask that no one gets too deep on their questions with that because it's going to go right over my head. I am but a simple beam jockey. And just as an example of what we might be looking for, this is, if any of you have ever used a gamma spectrometer, and forgive me for interspacing those terms, the X-ray and gamma ray, they get kind of fuzzy in some of these energies. This is just what you would get on it on the spectrometer showing across energy ranges. You get this antimatter peak, Compton edge, backscatter from it. And so this might tell you that there's some areas to also avoid. A civilization may not want to use the antimatter peak, for instance, because there's a lot of background in that. That's just everywhere. And these are the list of all the files that Lucas sent through, everything from a simple image all the way down to a wave video to try all sorts of different compression techniques and file types to prove himself out. And then sent it into this simulated gamma spectrometer to get these different signals. And we end up with this plot with the random signal and real signals, and these are the absolute entropy, not the relative entropy, which looks disappointing. When we look at the relative entropy, though, it immediately leaps out. You can see blue is relative entropy of the real signals, and orange is the random signals. We have no idea what those are. The code was not built to have any preconceived knowledge of what it's seeing, but you can tell that that is not a random X-ray or gamma ray background from the universe just by looking at the entropies of these signals. So then how do we do analysis on this? We don't know the pulse duration. We don't know the encoding. We don't know anything. In all likelihood, we're probably, if we're lucky, we'll just be listening in on someone else's communications. We're trying to catch their tweets or something. But we can scan across the phase space, which is what this plot is showing. We're sweeping through bit lengths and pulse durations, and you can see some discontinuities. So there's points where we don't get as clear of a relative entropy signal, but we do have a pretty far area to look. And no matter what, even as you start getting closer to random, you still, this is a log scale, so we still get very obvious signs that this is an artificial X-ray signal every time. And this plot is just an MPG. And so Lucas then scanned through the phase space as much as possible for a realistic detector. These two plots show parametric sweeps over bit length and pulse duration for a compressed file. I believe, it was an MP4 file. On the left, we have the artificial signal. On the right, we have a random signal. And there's a big area where it's very clear that the relative entropies show you that you are getting an artificial signal. And that's very promising because it means that there's a lot of space to look. And this is all based on realistic detectors that we have right now. We don't have to develop some magic new X-ray detector because we're not trying to decode their signals. We're just trying to tell, is there a signal? And we're very good at detecting X-rays and gamma rays. We can single photon count them. So the implications for SETI, Lucas came up with this plot that I'll show here in a second, just assuming 250 to 250,000 communicating civilizations, and the incredibly optimistic assumption that they transmit to any planet that looks like it might have life to try and make friends. And you end up with this plot across where we're plotting photon energy versus number of total beams of X-rays detectable at any moment. And a couple notable lines on there. Blue is the EUV lithography that we use for our phones that I mentioned. This is a very prominent, portable, maybe not portable, but almost portable, well understood technology that you could imagine building a big rip-roaring laser to communicate with right now. We go to LCLS, which I mentioned that's that big, scary free electron laser, and all the way down into some more natural signals, but maybe they try and emulate those with other exciting methods like true gamma ray lasers or matter-antimatter lasers. And as you go down in energy, you see there's fewer and fewer beams that we might catch at any one moment, and that's just due to the beams are going to be tighter and tighter. So what this kind of implies is that maybe, depending on our assumptions about who's all out there may have been signals detected in the past that we just didn't see. There are gamma ray telescopes up there right now, but they integrate. None of them are fast enough to look for this. There are also rapid gamma ray detectors for nuclear weapons detection. They may have seen something like this and we have no idea. That data is not in the public domain. And because these beams are very bright, they're very easily detected compared to radio. So to conclude, it's clearly possible to discern whether one of these signals is artificial, which is very promising. And we only looked at the most simple form of modulation, just on-off, photon yes, no photon. There's, of course, AM, FM, phase modulation, probably other things I'm missing. If we have a fully controllable laser, we could interspace multiple photon energies, all sorts of very impressive things that you could scan through. And if someone wants to jump at this, I encourage you. You could apply machine learning. You could do all sorts of very impressive signals analysis as to what to look for. This was just kind of a first pass at it. And this could provide a partial answer to the Fermi paradox in that we haven't heard anything from anyone because we're not listening. If we don't have our ears open, we'll never hear it, or see it in this case. And detecting X-ray and gamma ray beams with short time resolution is very doable today. Lucas proposes just using plastic scintillators. These are very robust, cheap, easy to get a hold of detectors that we have right now, and we could look for a variety of different photon energies and scan across some of this phase space, and you could make a spacecraft about 1 meter in diameter that we could launch tomorrow to go look for this. So maybe one of you will build it. Thank you for your attention. I'll take any questions.
Yeah, we have pretty good time around for plenty of questions if you've got to ask. Yep.
Maybe I missed it, but I didn't see what the bandwidth was.
You didn't miss it because I didn't have it on there. I will have to get back to you on that. It's definitely in the paper. And like I said, I kind of have to defer to Lucas. I just think about how to make the X-ray beams. But generally, bandwidth gets better as you increase the frequency of your photon source. And these are real high frequency.
Dial-up modem?
Yeah, it should definitely be better than a dial-up modem. We were talking megabits per second over hundreds of light years.
Okay. So is this suffering from the same problem that we talked about with the gravitational lensing? So it's very directional. So, or is it more like a broadcast, like you were saying, like a radio? If it's very directional, what's the likelihood of us actually intercepting it, and how far away you think we might need to get to actually catch it?
So it's incredibly directional, and that's kind of the point. That's why we think that it's the most likely way of trying to do communication for these distances. Maybe even within our own solar system, X-rays already have a serious advantage. As to the likelihood of detecting, we don't have to get out to the gravitational lens point or anything like that, thankfully. But it just comes down to your assumptions about, are they transmitting to life, planets that might have life? Or are we just right in between a colony and a home star? Or, there's a bunch of different ways you can do it. In reality, it runs into the basic SETI problem of just how likely are you to ever clip anything if someone's not trying to talk to you. But we should at least be listening in this whole new range that we're not looking for.
I had a question. I don't know if it would go too far into the information theory side of things, but can you tell the difference between different types of encrypted files that you're picking up by this method? And could you see if many different point sources in the sky are using the same kind of encryption, for instance?
So the relative entropies would tell you something about how data dense the file is. I don't think you'd pick anything else up other than that. But that might be a first step to break into the alien internet.
So tell us a little bit about, like, say, the Chandra X-ray Observatory or any other X-ray observatory you're familiar with, what the differences would be between that and something that would be able to detect a signal, or some evidence of a signal from another star.
Yeah, so the basic two important differences, although maybe we'll call it 1.5. Chandra, like any good telescope, integrates over a long period of time to get a very high resolution, and thus it would completely miss any of these modulated signals. It's just like if I was trying to do SOS to you with a flashlight, but you were looking with film over 1 hour, you wouldn't see a flashing light. You would just see one bright spot. So we would need a rapid response detector. And they just had no reason to have one for Chandra. They're looking all about resolution, or Fermi is another good example. So we would want a rapid response detector. The other thing is, arguably, you might want to make something that has no X-ray optics or gamma optics on it at all, because you're trying to detect from any direction. We have no idea where the signal's coming, and that's the advantage that our radio friends have, is that it's so easy to detect from any direction. But we also do that in the nuclear world. We can have just lots and lots and lots of these plastic scintillators around.
You suggest plastic scintillators for a quick experiment to look at this, but if you detect something, isn't part of your argument that, this is in an energy range where we expect it's artificial transmission, like the plutonium line that you were talking about, right? Don't you want for detection something with pretty good energy resolution? Does the plastic scintillator do that?
Yes and no. It's not great for energy resolution. You could imagine having a satellite that has both, though. The plastic scintillator, so the detectors that have great energy resolution tend to have poor response time. So you end up with this trade, and it's common to any detector world. Everyone is familiar with this. I think you're right. It would probably be good to have a satellite that is equipped, or maybe multiple satellites equipped to look for multiple different things.
Mm-hmm. Just when you want to have something that if you see a signal will convince everybody else that you should be allowed to look harder.
Yeah, that's very true.
So I was actually thinking about the question asked by Matthew here earlier on concerning the possibilities of discerning different kinds of speakers from the encrypted data, even if we cannot encrypt it. But I was thinking, could we not actually decipher it? If we see a bunch of messages with similar informational density, could we not make the tentative leap that they are the same language encoded in the same way, and so be able to distinguish them from different populations with different informational densities, which could presumably be another language encoded in a different way? I'm being completely hypothetical. You know perfectly well that I'm not a mathematician dealing with entropy or cryptography.
So I'm not either. And I would say maybe. That's very far out of my field. The most I can tell you is how to detect and make these beams.
More than acceptable.
Oh, I was just wondering from an engineering standpoint, if we're going to the emitter at, let's say, Alpha Centauri, who transmitting, a few TV show, equivalent of a few camera feeds, would be in what kind of range? Are we talking watts, kilowatts, megawatts, gigawatts?
Oh, Alpha Centauri, tens of watts. We could do that right now. That CXFEL machine that I showed you, which is being built right this very moment, would be what I would propose for it. And tens of watts of X-rays. Hopefully we can get some big heavy launch and get it up there, because it's going to be, probably need some cooling and things like that. But we're not. It's nothing far off in the future. It's all quite doable.
Yeah, we do actually have time for one more question if there's...
Gerrit, since you've solved the problem of making an X-ray beam for communication, can you develop an X-ray-driven light sail for us?
The X-ray optics are not good enough for that. They tend to be quite lossy, and they do not reflect nicely like light sails do. It's all glancing incidents. Maybe at the lower fuzzy end of X-rays you could, but also if Phil's in the crowd, the lasers that Phil uses are really, 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 really efficient. We're not that bad, but 1 or 2% sure starts to hurt if you want a gigawatt.
All right. Thank you very much, Gerrit.